Alright, CNT120, Chapter 1. We're looking at now some classifications of networks. So we're looking at LANMANWAN and some topologies of networks. Well, one way to classify a network is kind of the size of the network. What area does it cover? So this is where we run into the LANMANWAN thing. The LAN is your local area network, and it's basically, a network that's a relatively small space, a room of a building, a floor of a building, maybe even a house or a building. The Midtown building of Harrisburg, or the blocker building of the Harrisburg campus, if you will. And what I have is multiple computers and devices plugged into a switch, and that might be that might be it. That might look like my house, and that would be the LAN in my house. But it could be a larger switch. It could be a couple hundred devices still in my LAN, but it's still, maybe just that floor or that building of a company. Meanwhile, a MAN, a metropolitan area network, this would be where I have a network connecting multiple buildings in an area. A good example is most of us are sitting in or around the Harrisburg area, the capital of the state. So a lot of the government buildings in Harrisburg are connected by a MAN. So I might actually have a metropolitan network, some sort of fiber ring or fiber network connecting the government buildings in a city or a town. That would be a MAN, a metropolitan area network. Meanwhile, a wide area network, a WAN wide area network, is used to connect LANs at separate offices. So, okay, the LAN at Harrisburg, the LAN at Lancaster, the LAN at Lebanon, LAN at Gettysburg, the LAN at York, all connected together with WAN links to make the HAT network, if you will. So now I might have a LAN in, site A, a LAN at site B, and I'm using a WAN link between them. Here they're showing San Francisco and Philly, but this could be Harrisburg to Lancaster, for an example. That would be a WAN. So that's describing kind of the geographic area. Another way to categorize is by the topologies. We mentioned this way back earlier in the chapter. Now we're going to dig in and do some detail of. Well, I'm going to give you some more information the book is giving you. The book briefly mentions that, but I want to kind of go through real quickly the different topologies. Well, the bus topology started back in this day, very, very early Ethernet networks, where they used coaxial cable to connect the computers together. And if I go way back in time, it used thick coax cable, thicker than you have in your house, and vampire taps. This was a transceiver that bolted around the coax cable, and in here was a metal pin that actually pierced through the insulation, made contact with a copper conductor inside. They called it a vampire tap. Yes, just like a vampire fang. The vampire tap made contact into the copper conductor, and all the computers through the transceiver would make contact with this central coax bus. Well, eventually that was replaced with the thin coax, thinner than you have in your house, with BNC connectors, twist lock connectors, to connect them together. Much less intrusive than doing the whole vampire tap thing, much easier to deal with, but I still have that bus topology. And it was all because of Bob Metcalf. He was the one that had the brainchild to kind of do this, and this was actually his concept drawing that he drew for tapping into this central coax, the central media, tapping into it so all the computers could share information. That was your bus topology. It was inexpensive, but the downside is it did not scale well, difficult to troubleshoot, not very fault tolerant. You have one bad connection, it could potentially bring the network down in clogging the network with bad data, if you will. This was in kind of the 1980s ballpark when Ethernet was developing its network. Xerox was developing its network, which we call Ethernet today. That was the bus topology that was used for Ethernet. Well, meanwhile, IBM was developing a network for its computers called a token ring that used a ring topology. This right here. All the computers connected into a ring. Well, they did it using a different type of cable called STP, shielded twisted pair, and all the devices connected into this MAU, multi-station access unit. And these cables connected to the MAU, and the way the MAU worked is it literally passed a little data frame out to each computer and back. Data frame out and back, data frame out and back. Well, that little data frame called a token was kind of like a little shuttle bus driving around the city. It went to every computer and back, every computer and back, every computer back, and making a giant loop all day long. Well, that little token was designed to be like a little shuttle bus. If you had data, you put it on the token, it transported it to the node it needed to, delivered it, and it kept going in a circle all day long. That was your ring topology, your token ring network using a ring topology. This one here, there was no collisions the way it worked. But the downside is one simple malfunction and it literally disrupts the whole ring. It all falls apart. Not very flexible. It did not scale well. The more nodes you added, the bigger the ring got, the slower the transmissions, if you will. The larger the ring, the more nodes, the more time it took to transport the data. Meanwhile, Ethernet eventually went away from the bus topology into a star topology, and all the nodes were connecting into a central device. The original was a hub, all the devices connected to this central hub, and now we got rid of that coax bus and we now have twisted pair star. Well, the twisted pair cabling is much easier to deal with, cheaper to deal with, much easier to terminate, much easier to deal with. And now that all the devices are plugging into this hub, each of these little hub ports has a little blinky link light on. So now I actually have a little bit of idea on if there is a problem, where the problem might be. I don't see a blinky link light over 12. I know there might be a problem with the run for computer 12, if you will. That actually helped me out. Up to this point, you don't have that on pretty much any network component. And that's where we start moving into the star topology. And networks today are still using, Ethernet still uses a star topology. And for that reason, it is more fault tolerant. If I have a fault on actually, let me back up here. If I have a fault on this network link here, it only affects this network link. It does not affect the other ones. So it's a little bit more fault tolerant, a little more flexible, a little easier to troubleshoot. Again, I start getting what I call blinky link lights over each of the ports to give me some kind of clue as to whether it's working or not. Disadvantage, it does actually require more cabling. You have to have a cable run for every device that's connecting in. That adds up. And I do have a central point of failure. If this central device here fails, the whole network's pretty much done. Unless I have some redundant component built in or added into my network. But that is a central point of failure. That's your star topology. The book mentions those. I'm going to throw one more in the pile called a mesh topology. Now, you don't normally find a mesh topology between computers, but where you typically find is a mesh topology where I might have redundant links between my sites. Again, I could think of this as Lebanon, Lancaster, York, Gettysburg, that sort of thing. I might have more than one WAN link between these campuses. When I do, that's giving me some redundant connections. If something fails, I have another path to go. If this one fails, I can still route the traffic over to here, then to here. It'll get there. It might take longer, but it'll get there. Well, the mesh topology is more fault tolerant, but it's also more expensive. I have to buy those redundant links, and that adds up. But that is another topology you might run into. It is fault tolerant. I can load balance my traffic, but it requires more cabling, more lease lines, and it's going to be more costly. But I do run into mesh topologies, so it's one of those. It's worthwhile to stick in the back of your brain. The other thing I'm going to throw in the pile right now is backbone networks. They mention here backbone and backbone connections. Your backbones in a network are typically the high throughput connections between my switches or my routers, or between my closets in a building. So all my nodes connect into a switch. Well, when I connect from switch to switch or switch to router, that's usually going to be a high bandwidth connection. That part of my network is typically the backbone part of my network. Between closets, between switches, between the inter-networking devices. That's typically my backbone. And here I give you a reminder, if I'm sending 100 meg to my desktops, my backbone is usually 1,000 meg or higher. If I'm sending a gig to my desktops, my backbone head better be 10 gig or higher. So that gives you an idea. That's the high bandwidth part of my network, and that's usually the connections between my switches, routers, those kinds of devices in my network. All right, so I have a couple different backbone topologies, and again, I'm putting these out here as a kind of a put on your back burner for now, but at least you will have recognized when they talk backbones, this is what they're actually talking about. Well, I can hook up my backbone in a serial or daisy chain fashion. And when I do that, I'm literally just hooking my switches up, switch to switch to switch in a giant old line. Here'd be another example. I drew this kind of representing excuse me, the floors at the Midtown building. You know, the top floor, the second floor, first floor. If I connect my switches just right from switch to switch to switch, it's nice, easy connections. I'm not using many cables. I'm not using many device ports. But I also have the problem of if this link fails here, floor 2 and floor 3 is done. If this switch fails, floor 2 and floor 3 is done. I have many points of failure. And I also have points of log jams. All this traffic here has to go through this one. All of this traffic here, second and third floor, has to go through this link and this switch. So I start getting some bogging down and log jams down here, significant. So yeah, it's easy to implement. It's very low cost, not many cables, not many ports. But I start getting the bottlenecks and device failures and single point of failures and so forth. Most places do not use that because of these reasons. One of the next ones they mentioned is a distributed backbone. Well, distributed backbone, I'd actually start, instead of just connecting the switches together, I start using something like routers. Routers are more intelligent, so they can make better path decisions, and maybe even more secure. I should say they can be made more secure, so they might be able to add some security to my network. And again, here's my 3-floor building. Instead of connecting switch to switch to switch, I use a series of routers out here to connect my floors together. What that's doing for me is each router can act like a little mini toll gate or a little mini gateway or a little mini traffic cop, if you will. It's going to decide where things go and also if it should go. And if I add this extra connection, I actually have a little bit of redundancy. If this link fails, okay, this traffic can go this way. If this link fails, well, this traffic can actually go the long way around, but it will get there. So I have a little bit better reliability. But I am adding 3 expensive devices, and I'm adding 3 devices that will take longer time-wise to make decisions. A router takes a fraction longer to make a decision than a switch does. So it is adding some latency into my network. So I'm adding security, I'm adding some intelligence to my network, but the downside is I can have still potential single points of failure, but I can add in, that extra link to make up for that. But I am adding some latency because it's layer 3, and I'm adding costs because of those routers. A collapsed backbone, this guy here, this is actually a better example here. What I'm doing is, instead of having a router on each floor, I have one good layer 3 or 4 device. In this case, I have a layer 3 switch. All of these switches, being layer 2, are going to get combined into a layer 3 switch and then out to my router and out to the ISP. This is pretty common. This is what a lot of businesses or buildings use. So all the switches on the floor is combined into a layer 3 switch. A layer 3 switch has more intelligence. It's able to route, or it's able to do decisions based on IP addresses. Let me put it that way. It's able to make decisions about the data looking at the IP address when a normal switch cannot. A normal switch only looks at the MAC address, layer 2 address. So this has more intelligence. I have an individual link from each floor to this switch. So if one link goes down, it only affects that floor. So this is kind of like the middle of the road. This collapsed backbone is the middle of the road for kind of fixing all those problems that we were mentioning in the other ones. This is a very common backbone mechanism, or method, if you will. Central management layer 3 switch can act as, some intelligence in the network and route data through very accurately and very intelligently. I still have that central point of failure if I'm not careful, and I still have a bottleneck if I do not have a good layer 3 device there. The last one is a parallel backbone, where I'm basically going to double up everything down here. Now, I showed massive doubling up. I might just have a double layer 3 and a double firewall. I might not have all these extra connections, but the idea is where I had the limitations before, I'm adding redundant devices, and I'm probably going to have redundant firewalls and redundant ISP connections here to make up for all those deficiencies I had in the collapsed backbone. So it would be a parallel backbone. Redundant links, increased performance, better fault tolerance, but I have the added cost of all those things. All right, when we come back in the next one, we'll talk about some hardware in our network.